Welcome back to ACER Explained. In this video series, I'm going through section 3 of ACER's new practice test booklet. So bring that up in front of you if you haven't already so that you can follow along. In this video, I'm going through questions 8 to 10, so unit 3. As usual, I'm identifying prerequisite knowledge that you might need, reasoning skills used, and bootcamp resources as well. Okay, so this looks like a huge stimulus. However, it's very important to be systematic and not get too overwhelmed. I know it's easier said than done, but trust me, we're going to go through it and break it down, and it's not going to be as daunting as it looks initially. All right, so just looking at the stimulus, we're given some information about an electron beam and radiation. We're also given a diagram that shows how deep this electron beam goes. So this electron beam is in terms of radiation therapy for cancerous tumors. So the diagram is showing us how deep the beam can go in terms of proportions. It's given us two different radii, and that would be the kind of field that's affected by the radiation. So that's kind of the circular area that's affected by the radiation. And that's all we'll look at for now. That's kind of what we know for the diagram for now. Don't need to go too much into depth initially. Figure 2 is basically showing us the percentage depth dose for different beam energies. So there's 7 MeV, 9 MeV, 11, etc. And how far below the surface of the skin it can go. That's what's on the x-axis. So just with graphs, just take note the different colors. What do they mean? The x-axis and the y-axis. Then move on to the next bit. We're given some dot points about some assumptions that we are to make. It says assume the edge of the field occurs where PDD equals to 10%. And so that's important for question 8, which we'll find out later. But just know that that information is there. Then we have isodose curves, so figure 3 and figure 4. And that's for two different electron beam energies, 9 and 20. That's all we need to know. Okay, just noting where the information is. Then we look at question 8. Question 8 is asking us basically when electron beam energy increases, how does this affect the maximum depth under the skin at which the tissue is going to absorb radiation? And how is this going to affect the field size as well? So going back, we have 3 figures that are referring to, or they relate to increasing electron beam energy. That's figure 2, 3, and 4. So looking at figure 2, you'll quickly realize that you're not going to get too much information about the field size. However, you can see that the maximum depth is increasing as the electron beam energy increases. So the field size, the depth is increasing. So we can eliminate options A and B because options A and B are telling us that the depth is decreasing. So that's incorrect. So we have these 2 options left. Then we need to look at the field size. And the field size is shown in figures 3 and figure 4 because it's saying what the distance from the central axis is. So again, we have to go back to, where did we see central axis? We saw it in this figure. So this is the central axis. And the distance from the central axis is basically going to be the radius, okay? And so an increasing radius is going to mean, increasing field size, okay? And increasing radius is denoted basically in these graphs with distance from, because this is a circle, from central axis. And so we can see that when the distance from the central axis, when we look at the two graphs, one for 9 and one for 20, the distance from the central axis of the edge of the field, which we know is 10% because we remember that dot point says assume the edge of the field occurs when PDD equals to 10%, or the distance is equal to 10%. At 10% with the 9 MeV electron beam, it's at around, let's say, 6.1 centimeters. And with 20, it's around, let's say, 7, almost 8. Let's say 7.8, and we'll do 6.2 for this one. So as electron beam intensity increases, the field size also increases. And so we can say that the correct answer is answer D. For this question, you didn't actually need any previous knowledge. All of the information you needed was in the stimuli. But the reasoning skills that you used would have been interpreting large stimuli, interpreting graphs and diagrams, as well as extracting relevant information. These are very important reasoning skills. And so the bootcamp resources that can help with these are the reasoning skills course, the acceleration classes on introduction to diagrams and visual stimuli, graphs, and chunky text. So those are 3 acceleration classes that could be helpful for this. So question 9 is asking us about SSD and STD. So where did we see that? We saw that in that initial figure above, and then also in the dot points underneath figure 2. So SSD is referring to the source to skin distance, and then the STD is referring to the source to tumor distance. Okay, so I'm going to quickly just roughly draw out that little diagram. So we have kind of a cone-shaped projection here. Okay, so over here we have the tumor, and this is represented by AD. This little this circle here is represented by AD. Then we have another circle up here, so a cross section of that cone, which is AO, and that's referring to this level of the skin. This is referring to the level of the tumor. Okay, then we have 2 distances that we're given. Okay, so we're given SSD, and then we're given STD. So STD stays the same, the exact same. All right. We're basically being asked how the different distances are going to affect AO and AD in terms of like the different circle sizes. Okay. So if STD is staying the same, then AD is also going to stay the same, right? So because it's measuring from the starting of the beam to this particular point, which is AD. And so if this distance stays the same, then this is also going to stay the same as long as the electron beam has the same energy. If the electron beam had different energies, that could impact the field size and the depth, as we figured out in our previous question. However, if we're just looking at the 20 MeV beam, then as long as the distance stays the same, AD should also stay the same. Now we're going to look at SSD. So SSD is smaller than shown in the images. So basically this distance decreases. So let's say it was up to here now. Now, just from knowing the nature of a cone, we already know that this circle here is going to be smaller than this circle here, right? Because as a cone progresses downward, the radius of the cross section is going to increase. So this is going to be our new AO, and that AO is going to be smaller. So then we can look at our answer options. We have AO will be smaller, yes, but AD is going to be the same as we discussed. So this is incorrect. AO will be smaller, yes, and AD will be the same. Yeah, so the answer option is B. Over here, it's saying that AO will be the same, and that's incorrect because we know that if SSD decreases, then AO is going to be smaller. So that's the answer. The answer is B. I won't spend too much time on this because it's the same as the previous question. You don't need any previous knowledge, and the reasoning skills that you need is being able to interpret large stimuli, get the relevant information, and be able to interpret graphs and diagrams. Question 10 is a little bit more tricky. So I've just put up the diagrams and graphs, a rough version of them up here so that I can refer to them. It's basically asking if, it's a similar thing to the last question, if STD is smaller, but SSD is the same for specifically the 20 MeV beam, which of the following is most likely? And just taking a look at the answer options, it's asking us to look at the isodose curve and also asking us to think about the radiation dose that the tumor is going to have. So, STD is this distance here. Now, if that decreases over here, then this is kind of like the visualization of where it's going to be. Okay, this would be the new STD, and SSD would remain the same. So what does that really mean? It means that this over here, SSD, that's the distance from the point that you actually are pointing the radiation from, the electron beam from, to the skin. So here, this is the patient's skin, okay? And so a smaller STD, but the same SSD, what that means is that the tumor is essentially closer to the surface of the skin. If it was over here, then it would be deeper, right? So that's just a little bit of context. Then we want to look at the isodose curve for the 20 MeV electron beam. So what is the isodose curve actually showing? It's basically showing us different PDDs, right? And so the PDD is the percentage depth dose. And that's essentially the percentage of the maximum absorbed dose that could be possibly absorbed, right? So if it's less, that means that the tumor is getting less radiation is being absorbed by the tumor, essentially. If it's closer to 100%, it means that the tumor is absorbing closer to 100% of the radiation that you're being given, so it's getting a higher dose, okay? So that's what PDD means. And the isodose curve is just showing kind of proportions. It's just showing that if the tumor is 10 centimeters below the surface of the skin, it's gonna get however much PDD this is. Let's say that it's 10%. Say that perfectly matches up. Then at 10 centimeters below the skin, you're getting 10% of the percentage depth dose. Whereas if you're closer to the skin, so say you're getting, we'll say that it's over here, 3 centimeters, then you're getting 90% of that percentage depth dose. And actually these curves go around here. So if it was 0 as well, you'd be getting, if it was 0 centimeters, you'd be getting 90% because that's the maximum, right? So it's kind of showing proportions, and therefore changing this distance is not going to change this entire curve, but it's going to change what you take away from the curve. So the isodose curve is actually going to be the same, because the isodose curve, if you compare figure 3 and figure 4, only becomes compressed or expands when there's a difference in energy level of the electron beam. So that's the only thing that's going to compress or expand the isodose curve. So over here, we can eliminate this and we can eliminate this because the isodose curve we know is going to stay the same. Then we have to look at the radiation dose. So looking over here, we have, is the radiation dose going to be the same, or is the radiation dose going to increase? So if STD is decreasing over here, then basically what we inferred from this diagram is that it's going to be closer to the surface of the skin. It's going to be less deep, right? So say we started off over here. Now, so let's say that was like 4 centimeters. Now it's going to be up here at 3 centimeters. And so rather than being exposed to 50% PDD, you're going to be exposed to 90% PDD. And what does that mean? That means that the percentage depth dose has increased. And so the amount of radiation that's actually being absorbed by the tumor as a percentage of the total radiation has increased, right? And because the radiation is the same, the level of radiation is the same, then what we can conclude is that a higher percentage of this compared to a lower percentage of this is going to be an increased radiation dose. Does that make sense? So the radiation dose is going to increase. And that logically as well makes sense. If the tumor is closer to the skin and the distance that you're holding your electron beam from the skin is the same, then the tumor that's closer to the skin is going to get more radiation than the tumor that's really, really deep in your skin, right? So that hopefully is a bit of reassurance for you for selecting option B, and then you can move on to the next question. So same as before, there was no prerequisite knowledge required here. However, this was quite an intimidating stimulus because of the different diagrams and graphs and the amount of information that you're being shown. So being able to work through it systematically, like I mentioned at the very beginning of this unit, is very important so that you can keep a level head and just extract the information that you need and answer the questions with that information. So again, same reasoning skills and bootcamp resources as I've been mentioning for the previous questions, but this is an excellent example of a question that could come up in the GAMSAT, and how you can actually use reasoning to solve it, and how you don't actually need those that any knowledge about tumors or any knowledge about radiation or physics in this case. There's no physics here as well. It's pure reasoning. So that brings us to the end of Unit 8. Please like, share, and subscribe, and give us feedback. We really value it. And our Instagram is there at Thank Flip GAMSAT, and we have our podcast at Thank Flip GAMSAT Nurses Doing GAMSAT if you want to hear more from us. All right, I'll see you in the next one.